Okay, so today we're going to talk about um, the last trend on the periodic table that I'm really going to be speaking about, which is ionization energy. So, first, I'm going to go over something called, you probably heard of before, electromagnetic radiation. So, we're going to talk about that real quick. Okay, so electromagnetic radiation, if I could spell this, that'd be great. Um, Electromagnetic radiation is a form of energy on the electromagnetic spectrum. On the electromagnetic spectrum. Okay, so if an atom absorbs energy, electrons become excited, moving to higher energy levels. We've already learned this. That's absorption, emission. So I'm going to essentially redraw that just so we can go over that again. So let me do this so it's all nice and neat. It's going to take a second, so just bear with me. I just want everything the same. Okay, so we have one, and then let me make another table, and boom, same. All right, so we have absorption over here. And emission. Okay, so when one more thing I forgot to do because I'm like rushing. We have our energy levels. I'm just going to do the first four. It's fine. Okay, so we have energy from wherever, and it's beaming right at an electron. So what happens is, say we had one here, and it absorbs it. It's going to be able to move to a higher energy level. Where it falls, I don't know. It's completely random. So it has to do with the amount of energy that it absorbs. So whenever energy interacts with electrons in an atom, it moves them to a higher energy level. You can kind of think of it as like an onion. That's not really how it's represented at all. In actuality, they look like, if I could, a sine wave, I guess would be the most accurate way to describe it. So it just looks like this. That's like your electrons, but for simplicity's sake, we're going to go with the onion model from Niels Bohr that was, expanded upon by other scientists. So, anyways, when you have an electron that's excited and it's got a bunch of energy pent up, it's got to let it go to go back down to a ground state. So that's when we have something called emission. So when emission happens, that energy has to go somewhere as the electron falls. So it kicks it out in the form of a photon, which is pretty much just light or electromagnetic radiation. So you can take a second to copy all this. Pause the video. I'm going to move on. This is going to be a pretty short video. It's not too complicated. So now we're going to talk about ionization energy. That was important to talk about this. So ionization energy. Okay, so ionization energy is the amount of energy required to remove an electron from an atom. So let's write that down. The amount of energy required to remove an electron from an atom. Okay, so ionized means it has lost one or more valence electron. So atom has lost, cannot write, has lost one or more valence electrons. That's all it means. So that's pretty much the definition for ionization energy. I'm going to go over quickly group and period trends, and then we'll be done. So, all right, group trends. Tried to stay consistent with the colors. So, the bigger an atom is, the lower its ionization energy is. So, as you go down a group, the ionization energy decreases. There's a reason for this, and I'll explain it after I go over the period trends. Oh, not larger, lower. So, as you move down a group, the ionization energy decreases. There is a way to kind of calculate this from tables. I'm not really going to go over it. I mean, it's pretty easy, but I might show you in class. Not a big deal. Really, it's a way for you to tell like when it's ionized. Anyway, so period trends. So as you move from left to right across a period, the ionization energy increases. Okay, so think for a second. Why would you think that in the group trend, the bigger an atom is, the lower its ionization energy is? And in the period trend, as you move left to right, why that energy increases? So think for a second before you watch me explain it, because I want to see if you can, show yourself that you know it. So in a group, the group trend, as you get bigger and bigger atoms, you can kind of think of like bigger and bigger orbits. It's further away from what's pulling those electrons close to it. So it's easier for, this atom to lose an electron as opposed to, this atom. Like, it's just way easier because it's further away. It's got less of a hold on its valence shell. It's like, you could think of it as like Jupiter having, like, I don't even know how many moons. It's got a lot, though. And just somebody takes one of the moons and is like, yep, I'm taking that. Granted, with our current technology, that's probably super impossible, but like as a thought experiment, it'd be rather easy because it has a gravitational hold on it, just like this has an electromagnetic hold on it. But the fact is, it could lose that electron and be fine. Whereas the further left and right, like as you go from left to right, the further right you go, the more pull it's going to have on that valence shell because your nucleus is getting more positive. So it's going to be a little bit harder in the same period, mind you. It's going to be harder for a valence electron to leave. So this is going to come into play when we start talking about like ionic compounds, chemical reactions, acids and bases, like all this comes into play. But I just wanted to kind of give you a quick overview about it. So that's pretty much it for the video. If you have any questions, please reach out to me, and I'll see you in the next video.